Good morning everyone. The topic of the lesson is Complex Numbers, Chapter 1. My name is Toksanova. I am math teacher at Nazarbayev Intellectual School of Physics and Mathematics Directions in Kokshetau. Learning objectives. By the end of the lesson, you will be able to understand that new number systems can be created provided that the definitions are algebraically consistent. Be able to do calculations with complex numbers. Know the meaning of conjugate complex numbers and that non-real roots of equations with real coefficients occur in conjugate pairs. Be able to solve simple equations with complex coefficients. Task number 1. Consider the quadratic equation x squared plus 1 is equal to 0. Solving for x gives us x squared is equal to minus 1. From this, x is equal to square root of minus 1. We make the following definition: I is equal to square root of minus 1. Before, we would say that this equation doesn't have any real roots. Now we create new number systems, complex number systems, so that the square root from negative number exists. Definition. The complex numbers consist of numbers of the form a plus bi, where a and b are real numbers, and I squared is equal to minus 1. Complex number. In Kazakh, kompleksan, in Russian, комплексное число. So, complex number consists of two parts. Real part, in Kazakh, нақты бөлігі, in Russian, действительная часть. And imaginary part, in Kazakh, жорамал бөлігі, in Russian, мнимая часть. Definition. The complex numbers consist of numbers of the form a plus bi, where a and b are real numbers and I squared is equal to minus 1. Complex number in Kazakh, kompleksan, in Russian, комплексное число. Complex numbers of the form a plus 0 multiplied by I are called real numbers. There is no imaginary part. And complex numbers of the form 0 plus bi are called imaginary numbers, because there is no real part. Real number. Sometimes we say pure real number. In Kazakh, нақтысан, таза нақтысан. In Russian, действительное число. And imaginary number, sometimes pure imaginary number. Жорамалсан, таза жорамалсан in Kazakh. And in Russian, мнимое число, чисто мнимое число. Real numbers and imaginary numbers are subsets of the set of complex numbers, as you can see from the slide. Example of complex numbers. 1 plus square root of minus 8. We can rewrite square root of minus 8 as a product of square roots of minus 1 and square root of square root of 8. We know that square root of minus 1 is equal to I, and square root of 8 we can rewrite as a product of square root of 4 and square root of 2. We know that square root of 4 is equal to 2. So the final result is 1 plus 2i multiplied by square root of 2. Complex numbers application. Since complex numbers provide a system for finding the roots of polynomials, and polynomials are used as theoretical models in various fields, complex numbers enjoy prominence in several specialized areas. Among these specialized areas are control theory, improper integral, fluid dynamics, dynamic equation, electromagnetism and electrical engineering, signal analysis, quantum mechanics, and relativity, geometry, algebraic number theory, analytic number theory. Topic utilizing complex numbers include the investigation of electrical current, wavelength, liquid flow in relation to obstacles, analysis of stress on beams, the movement of shock absorbed in cars, the study of resonance of structures, the design of dynamos and electric motors, and the manipulation of large matrices used in modeling. Introduction to the history of the complex numbers. The solution in radicals of a general cubic equation contains the square root of negative numbers when all three roots are real numbers. A situation that cannot be rectified by factoring aided by the rational to root test if the cubic is irreducible. This conundrum led Italian mathematician Girolamo Cardano to conceive of complex number in around 1545, though his understanding was rudimentary. Work on the problem of general polynomials ultimately led to the fundamental theorem of algebra, which shows that with complex numbers a solution exists to every polynomial equation of degree 1 or higher. Complex numbers thus form an algebraically closed field where any polynomial equation has a root. Many mathematicians contributed to the full development of complex numbers. For example, Euler's formula states the trigonometric form of the complex numbers. We use it nowadays. And de Moivre find out the formula for the multiplication and division of the complex numbers written in the trigonometric form. Now we are going to consider the calculation with complex numbers. 4 of them you can see on the slide. Addition, in Kazakh хосу, in Russian сложение. Subtraction, in Kazakh азайту, in Russian вычитание. Next, multiplication, in Kazakh кобейту, in Russian умножение. Division, in Kazakh бөлу, in Russian деление. We will consider 4 of these calculations, 4 arithmetic operations, and we will consider involution, raising to a power, and square root of complex numbers. Let's start from addition and subtraction. By the usual rules of algebra, when we add or subtract two complex numbers, we remove the brackets and then we group real and imaginary parts. So real part is a plus c or a minus c, and imaginary part b plus minus d, since a, b, c, d are real numbers. So to add or subtract two complex numbers, we should add or subtract their real and imaginary parts separately, and then add their results. The expression at the end of each line therefore has the form p plus qi, where p and q are real numbers. Let's consider the example for addition and subtraction of complex numbers. If r is equal to 3 plus 5i, and s is equal to 1 minus 4i, find their sum and their difference. To add two complex numbers, we add their real parts. 3 plus 1 gives us 4, and we add imaginary parts, 5i and minus 4i, which gives us I. So the final result of the sum of given two numbers, 4 plus I. The same we do when we subtract two complex numbers, r and s. We subtract real parts, 3 minus 1, which equals to 2, and we subtract the imaginary parts, 5i and minus 4i, which gives us 9i. So the final result is the difference of two complex numbers r and s is equal to 2 plus 9i. Uniqueness. If a plus bi is equal to 0, then a is equal to minus bi. So we can square both sides. A squared is equal to minus bi squared. We know that I squared is equal to minus 1. So a squared is equal to minus b squared. Now a and b are real numbers. That a squared is equal or greater than 0 and minus b squared equal or less than 0. They can only be equal if a squared equal to 0 and b squared equal to 0 too. That is, a is 0 and b is 0. So, if a complex number is 0, its real and imaginary parts are both 0. Equality of complex numbers. Using previous slide, we combining this with the rule for subtraction shows that if two complex numbers a plus bi and c plus di equal, we can subtract them and this difference is equal to 0. Now we subtract their real and imaginary part. So a minus c should be equal to 0 and b minus d is equal to 0 too. From this, a and c are equal and b and d are equal. Conclusion: if two complex numbers are equal, their real parts are equal and their imaginary parts are equal too. Multiplication. By the usual rules for multiplying out brackets, we multiply a plus bi in brackets and c plus di in brackets. We remove the brackets and we get the real part ac minus bd, and the imaginary part is ad plus bc, since a, b, c, d are real numbers. The product is therefore of the form p plus qi, where p and q are real numbers. Task number 3. If r is equal to 3 plus 5i and s is equal 1 minus 4i, find their product. We remove the brackets and we group like terms, so the product of given numbers is equal 23 minus 7i. Involution. We know that I is square root of minus 1. Note that squaring both sides gives us I squared is equal to minus 1. Therefore, I cubed is the product of I squared and I to the power of 1. The first is equal to minus 1, the second is I, so their product is equal to minus I. And I to the power of 4 is the product of I squared and I squared. The first is minus 1, the second is minus 1 too, so their product is equal to 1. The next power, I to the power of 5, is the product of I to the power of 4 and I. The first is 1 and the second is I, so their product, or I to the power of 5, is equal to I. I to the power of 6 is equal to I to the power of 4 multiplied by I squared. The first is 1 and the second is I squared, which is equal to minus 1. So I to the power of 6 is equal to minus 1, is minus 1, and so on. We can continue it and we see the cycle. Minus square root of minus 1, then minus 1, minus I, and 1, and then it will be repeated. Multiplication. An important special case of the multiplication rule is a plus bi multiplied by a minus bi is equal to a squared plus b squared plus 0i, as you can see from the slide. So it is a real number because there is no imaginary part. It follows that in complex number algebra, the sum of two squares, a squared plus b squared now can be factorized as a plus bi multiplied by a minus bi. These numbers we call conjugate complex numbers. Their real parts are equal and their imaginary parts are opposite numbers, plus b and minus b. Definition. Complex conjugates a pair of complex numbers of the form a plus bi and a minus bi, where a and b are real numbers. Conjugate. In Kazakh түйіндес, in Russian сопряженный. The product of a complex conjugate pair is a positive real number. Properties of conjugate complex numbers. If s and t are complex numbers, any complex numbers, then the conjugate of the sum of two complex numbers is the sum of their conjugates. The same. The difference of two complex numbers is the difference on their conjugates. And the same with multiplication and division. You can prove it yourself. Division. First, there are two special cases to consider. When the denominator of a plus bi divided by c plus di is either a real number or an imaginary number. If the denominator is real, so that d is equal to 0, then a plus bi divided by c plus 0, a plus bi divided by c, we can rewrite it separately, a over c plus b over c multiplied by I. The second case, if the denominator is imaginary, so that c is equal to 0, you can simplify the expression by multiplying numerator and denominator by I. As you can see from the slide, a plus bi over di, we multiplied numerator and denominator by I, so we get b over d minus a over d multiplied by I. And the general case, to find the quotient of two complex numbers, multiply the numerator and denominator by the conjugate of the denominator. In this case is c minus di. We simplify numerator and get ac plus bd real part and imaginary part bc minus ad, and the denominator c squared plus d squared. Let's consider the example. Write as complex numbers in the form p plus qi. The first task 1 over I, and the second 1 plus 4i divided by 2i. The first task 1 over I. To divide 1 by I, we should multiply numerator and denominator by I. In numerator we get I, and denominator I squared, which equals to minus 1. So the final result is minus I. The second task we can solve using two methods. The first method is, as in previous task, we multiply numerator and denominator by I, and we get 2 minus 1 over 2 multiplied by I. And the second method, we can rewrite 1 plus 4i divided by 2i separately. 1 over 2i plus 4i divided by 2i. The last one gives us real part, which equals to 2. The second one is imaginary part. And it gives us the same answer, 2 minus 1 over 2 multiplied by I. Task number 7. Perform the operation and write the result in standard form. Numerator 6 minus 7i, denominator 1 minus 2i. To divide these two complex numbers, we should multiply the numerator and denominator by the conjugate of the denominator. So it is 1 plus 2i. We simplify and get in numerator 20 plus 5i, in denominator 5. We rewrite it separately, so the final result is 4 plus I. Task number 8. Perform the operation and write the result in standard form. It is more complicated task. 1 plus I over I minus 3 over 4 minus I. The same, we can do it, we can solve this task using different methods, but we will consider just one method. In first fraction, we will multiply numerator and denominator by I. So the first fraction, after simplifying, will be equal to 1 minus I. And the second fraction, 3 over 4 minus I, we multiply numerator and denominator by 4 plus I. After simplifying, we get 12 over 17 plus 3 over 17 multiplied by I. We subtract the real and imaginary parts separately. So the final result is 5 over 17 minus 20 over 17 multiplied by I. The last arithmetic operation, it is evaluating the square roots of the complex numbers. Complex numbers were introduced so that all real numbers should have square roots. But do complex numbers themselves have square roots? Task number 9. Find the square root of 8i and 3 minus 4i. The problem is to find real numbers a and b such that a plus bi squared is equal to given numbers. To do this, note that a plus bi squared is equal to a squared minus b squared, it is a real part, and imaginary part is 2ab. And remember that for two complex numbers to be equal, their real and imaginary parts must be equal. So we rewrite it: a plus bi squared is equal to 8i. Then we get a pair of equations with two variables, a and b. The first equation, a squared minus b squared, is equal to 0 because 8i is a pure imaginary number. There is no real part. And 2ab is equal to 8. It is imaginary part. Solving this pair of equations, we get two solutions. A is 2 and b is 2. And the second solution is a is minus 2 and b is minus 2. So 8i has two square roots, 2 plus 2i and minus 2 minus 2i. And the same we do in the second task. But here we have the whole of the full complex number. I call it full complex number because their real and imaginary parts are not equal to 0. Task number 9. Find the square root of 3 minus 4i. We do the same, rewrite it: a plus bi squared is equal to 3 minus 4i. Real part a squared minus b squared is equal to 3. And imaginary part 2ab is equal to minus 4. Solving these pairs of equations, we get a is equal to 2 and b is minus 1. And the second solution is a is minus 2 and b is 1. So 3 minus 4i has two square roots, 2 minus I and minus 2 plus I. Now we are going to solve different equations. Let's start from quadratic equations. Task number 10. Solve the quadratic equation z squared plus 16 is equal to 0. We should subtract 16 from both sides, left and right. So z squared is equal to minus 16. To get z, to find z, we should take square root from both sides. So z is equal plus minus square root of minus 16. We will write minus 16 as the product of minus 1 and square root of 16. We know that square root of minus 1 is equal to I, and square root of 16 is equal to 4. So the final result, the solution of the given quadratic equation is z is equal to plus minus 4i. Task number 11. Solve the quadratic equation z squared plus 4z plus 13 is equal to 0. Let me notice that all coefficients are real numbers. It will be necessary for us at the end when we will get the solution. Again, we will do it using two methods. The first method. In the usual notation, a is 1, b is 4, and c is 13. So that b squared minus 4ac, we call this expression as discriminant, it is equal to minus 36. Previously, you would have said that there are no real roots, but now you can write square root of minus 36 is equal to 6i. Using the formula of the root of the quadratic equation, we get z is equal to minus 4 plus minus 6i divided by 2. And the final minus 2 plus minus 3i. And once again, I repeat that the given equation has real coefficients. So their roots, the roots of given equation are conjugate complex numbers. Once again, solve this given equation by using another method. In completed square form, z squared plus 4z plus 13, we get z plus 2 squared plus 9. Then we factorize and find the roots of the given equation. And they are the same, minus 2 plus minus 3i. So these are conjugate complex numbers because the given equation has real coefficients. Now we will create quadratic equation using given conditions. You can find the complex conjugate of a complex number. Task number 12. Find the quadratic equation that has roots 3 plus 5i and 3 minus 5i. Using Weyer's theorem, we should add the roots together and the sum will be 6. So the second term will be minus 6. Then we multiply the roots and we get 34. So the third term is 34. Now we can write the equation with the given roots 3 plus 5i and 3 minus 5i. So the equation is x squared minus 6x plus 34 is equal to 0. Task number 13. Solve the quadratic equation 2 minus I multiplied by z squared plus 4 plus 3i multiplied by z plus minus 1 plus 3i is equal to 0. Let me notice that this equation doesn't have real coefficients. It has complex coefficients. So the roots of the given equation will not be the conjugate pair. Using the standard formula, we get a is equal to 2 minus I, b is 4 plus 3i, and c minus 1 plus 3i. Using formula, we get minus 4 plus 3i plus minus square root of the complicated expression, which you can see on the slide, b squared minus 4ac, divided by 2 multiplied 2 minus I, or the first coefficient. After simplifying, we get the roots minus I and minus 1 minus I. You can see the whole solution on the slide. In the first method, we use standard formula of the quadratic equation. Let me consider the second method. Now again we will use the standard formula, but before you can often reduce your work by first making the coefficient of z squared real. So we multiply through by conjugate of 2 minus I. It is 2 plus I. So the equation becomes 5z squared plus 5 plus 10I multiplied by z plus minus 5 plus 5I. We divided it by 5, and the final equation will be z squared plus 1 plus 2I multiplied by z plus minus 1 plus I, which is equal to 0. We reduce our work, and now we have simpler equation. Using standard formula, with A is 1, B is 1 plus 2I, and C is minus 1 plus I, which gives us the same roots. Whole solution you can see on the slide. So the given equation with complex coefficients has the same roots, minus I and minus 1 minus I. Conclusion. The fact that with complex numbers every quadratic equation has two roots is a particular case of a more general result. Every polynomial equation of degree n has n roots. Now let's solve polynomial equations. Task number 14. Show that x is equal to 2 is the solution of the cubic equation x cubed minus 6x squared plus 21x minus 26 is equal to 0. Hence, solve the equation completely. So you should find two roots of the given cubic equation. As x is equal to 2 is a solution, the equation must have x minus 2 as a factor of the given equation. Divide the expression by x minus 2 in order to help factorize it. And we get the second bracket of the power of 2, x squared minus 4x plus 13. We equate it to 0 and solve the usual quadratic equation. So the roots is 2 plus minus 3i. Answer. The solution of the equation x cubed minus 6x squared plus 21x minus 26 is equal to 0 are x is equal to 2, x is equal to 2 plus minus 3i. Task number 15. Given that 3 plus I is the root of the quartic equation. Let me notice that quartic means power of 4. 2x to the power of 4 minus 3x cubed minus 39x squared plus 120x minus 15 is equal to 0. Solve the equation completely. So this equation has real coefficients. So if 3 plus I is the root of the given equation, then 3 minus I should be the root of the given equation. Add them together using Weyer's theorem. The sum is 6, and the product, when we multiply them, is equal to 10. So the given polynomial of the power of 4 should be divided by x squared minus 6x plus 10, which gives us polynomial of the number of 2. 2x squared plus 9x minus 5. We equate it to 0 and using standard formula get the third and the fourth roots. Minus 1 over 2 and 5. So the given quartic equation have 4 solutions. 3 plus I and 3 minus I, conjugate complex numbers, because given equation has real coefficients, and 2 other roots minus 1 over 2 and 5. Solving polynomial equation. Task number 16. Solve the equation z to the power of 5 minus 6z cubed minus 2z squared plus 17z minus 10, which is equal to 0. Denote the left side by p and begin by trying to find some real factors using the factor theorem. Try z is 1. When we put 1 to the polynomial p, it is equal to 0. So z minus 1 is a factor of p. Write p as a product of z minus 1 and polynomial q, which has power of 4. Then rewrite it as a product of two brackets, z minus 1 and the polynomial of the power of 4. We remove the brackets and we get the set of equations. From this, a is equal to 1, b is 1, c is minus 5, d is minus 7, e is 10. So the polynomial q can be rewritten as a z to the power of 4 plus z cubed minus 5z squared minus 7z plus 10. Do the same to factorize polynomial q. Again, try z equals to 1. Put 1 into the polynomial of q, and once again it is equal to 0. So polynomial q can be rewritten as a product of z minus 1 and another polynomial r, which has degree 3. You can check for yourself that polynomial r is equal to z cubed plus 2z squared minus 3z minus 10. Continue in the same way, try to factorize polynomial r. This time, when we put 1, it is not equal to 0, but when we put 2, it is equal to 0. So polynomial r can be rewritten as z minus 2 and polynomial s, which has degree 2. You can check that polynomial s is equal to z squared plus 4z plus 5, which can be solved using standard formula or completing the square. So the given polynomial p has the roots 1, it is a repeated root, counted twice, 2, and conjugate complex pair minus 2 plus minus I. Summary. You have been introduced to imaginary and complex numbers. You have also introduced how to do calculations with complex and conjugate complex numbers. You have seen how this finally allows all quadratic equations to be solved. You have also seen how to solve polynomial equations using complex numbers. My references you can see on the slide. Thank you for your attention. Goodbye.